morning. We begin with a quick summary of lecture 19 and then move into the topics for today's discussion. The recap will basically consist of our case 4 and case 5 of Say and Vishwanath. I hope you've had a chance to look at the examples basically to summarize and gain insights into the different aspects of the wireless channel. We introduced our basic understanding of coherent detection and also some of the challenges with coherent detection. What happens in the presence of fading? And there were several questions after the lecture. So what I thought was we would spend about 10 minutes in today's lecture addressing some more aspects of coherent detection so that everyone, we will all be clear and have a good understanding of why, what are some of the challenges and why they occur and how they may be addressed in the context of a robust wireless system. So once we have done that, then we can talk about what is the other option other than coherent detection, or coherent modulation. That would be differential modulation with non-coherent detection, and then look at some of the differences between the two. That also gives us a basis to compare, for example, two very similar modulation schemes, coherent QPSK and non-coherent QPSK or differential QPSK. Both of them carrying 2 bits per symbol. Which one would you use? Which one would be better? Which one would be more robust in a wireless system? Those are some things that we will comment upon. Now comes the question of non-coherent detection. Yesterday we said, well, it's not suitable for channels with ISI. Why is it not suitable? Let's give a quick answer to that. Can you have hybrid? Can you do differential modulation and coherent detection? Can you do coherent modulation and differential detection? Again, interesting questions. The answer to that you should know as a student of digital communications and wireless. With this background, we will then start to look at the analytical expressions for bit error rate. Again, the analytic expressions give us a lot of insight, but we have to have the patience and the effort to actually go through the derivation of the analytical expression. So again, there is some level of integration and some techniques involved. The goal of our course would be to give you hints on those methods and then help you get to the final answer, interpret the answer, get insight, and then help us design good systems for wireless channels. We will also talk about one of the things that we have studied so far is the probability density function, probability distribution function for a wireless channel, which is characterized in the following form: Z of t, which is alpha of t e power j phi of t. Now alpha is the one that has got the Rayleigh PDF. And we have also said that the SNR in a AWGN channel is given by EB by N naught. Now if the amplitude is getting modified by alpha, then the signal power will be modified by alpha squared. So when we talk about PDF of SNR in a fading channel, SNR in a AWGN channel is a constant, but in a fading channel, SNR is not constant. You must specify alpha for it to say what is the instantaneous SNR. So what is the PDF of a fading channel, and how does that help us to estimate the analytical expressions for BER? So again, there is a fair amount of material that we would like to cover today. So first, to summarize, this is to conclude our discussion of the TNV example. Again, we looked at cases 1, 2 and 3. Case 4 was moving antenna plus reflecting wall. This was a combination that gave us that the E field in this case was a superposition of two sinusoidal components. Let me call that as signal 1. That's the first component. This had a negative Doppler because it was moving away from the transmitter. Then there was signal 2, which was after reflection, that had a positive Doppler. And these two were interacting to produce the resultant electric field. So the observation that we made was there were two Doppler shifted versions, that the FD max, FD stands for Doppler, the maximum possible Doppler shift can be plus or minus FV by C. V is the vehicle speed, speed of motion. I don't want to call it vehicle speed, basically either transmitter or receiver, one of them is moving, and the speed of motion of the moving antenna is V meters per second. V meters per second. Okay, so this also gave us that there is a notion of a Doppler spread, various components that can be received by the receive antenna, and maximum Doppler spread will be from the most negative to the most positive, that is 2 times FV by C. So in terms of the spectrum shifting, the spectrum can shift all the way to the left because of the negative Doppler, can shift all the way to the right to the Doppler. So when you have large number of Doppler components arriving, give me a spectral interpretation. What does your received spectrum look like? You have a received spectrum, which in the case of an AWGN channel would be a fixed one. Now there is a smearing of your spectrum because some Doppler components are shifting because of negative Doppler, some are shifting to the right, and the resultant. But from a filtering point of view, it did not pose a challenge because the receive filter will allow all the Doppler components to come in. Now as we said yesterday, where it's going to have an impact is in the time domain, and that is what we would like to look at more carefully today. So case 5 is basically case 4. This would be case 4 plus near reflecting wall. I basically, using short form notation, the receiving antenna is near the reflecting wall. So it turns out to be a special case. Again, you just have to apply the approximation near the reflecting wall. What we found was that both signal 1 and signal 2, because of both of them are approximately traversing the same one, signals 1 and 2 are approximately equal amplitude. Equal amplitude. That was one observation that we made. The second one, of course, was that one of the components has got maximum negative Doppler, the other one has got maximum positive Doppler. So basically 2 Doppler shifted versions. 2 Doppler shifted versions are available to us. They are actually interacting with each other. So the Doppler shifted versions will be FC plus or minus FD max. And we also showed through a numerical example that FD max in most of the cases that we encounter is substantially less than FC. So what we have is a superposition of 2 sinusoids that are very close in frequency. And then in physics we know that when this happens, there will be beating of the 2 sinusoidal components that results in a product of sinusoids. So this resultant is a product of sinusoids which has the sum and difference components. So of course you can look at it and recognize that there will be a component at FC and then there will be a component at FD max. So product of sum and difference frequencies. And this is what gave us the insight that we were looking for, which said that there is a carrier frequency at FC. There is a Doppler frequency. In our case, we saw FD max. Both of them interacted, so FC plus FD max. These two interacted with each other, and what we got was a product, a resultant, where the signal envelope is not constant. It's a fluctuation. So the observation is that in such a scenario, the E field fluctuates. That is one very important notion. And the rate of fluctuation is proportional to Doppler. Rate of fluctuation proportional to FD. In our case, it is FD max is what we are seeing. Okay? So that would more or less tell us how the system would have to be understood and interpreted. Okay, so this was the Sayan Vishwanath, and I hope all of the different elements, the coherence time, coherence bandwidth, coherence distance, the rate of fluctuation, all of these have given you some level of insight into what's happening into the wireless channel. Okay, then we said, given that we now understand what the wireless channel is all about, I want to look at what are the criteria for choosing a modulation. 4 things that we said. One would have to be, this basically is a slide from last lecture, acceptable BER. You know what is the SNR that you will get, or SNR, what is the corresponding modulation scheme that will give you acceptable BER. And the modulation scheme that we choose must be robust to the impairments. Impairments could be in the form of just fading. That means there is no time dispersion. There could be combination of fading and dispersion. That would be multipath ISI. Then it could also have interference from co-channel cells. Again, each of these has got corresponding signal processing techniques. We have, or techniques such as forward error correction. We should be able to implement them with reasonable complexity at the receiver. At the end of the day, how will we measure the goodness or the suitability of a modulation scheme? It will be through the selection of the spectral efficiency or estimation of the spectral efficiency, which would be given by bits per second per hertz. So that would be our goal. We also said not to forget that a very practical element would be the power amplifier efficiency, that it could offset the advantages that you get in terms of BER if you have something that gives you very good power amplifier efficiency. Okay, now let me just shift to the previous graph where there were a lot of questions. After the class, several students stopped by and asked, said, okay, you have a channel estimation happening whenever there is a training scheme that is, so basically there is an estimation that is happening here, an estimation that is happening here. This is less than coherence time. So why is the channel changing within the coherence time? So let me elaborate a little bit more. This was more of a dramatic description of what changed. Usually what that means is within the coherence time, the change is small, but there is change. So again, depends on the amount of Doppler that you have designed for. So for example, I assume that my system is designed for Dopplers up to 60 kilometers per hour. So I have designed my periods with the appropriate coherence time. Now, if you are traveling at 100 kilometers per hour, what will happen? You have actually your coherence time is much less. So therefore, there will be a change in the channel. So like that, there are some cases where between the estimates there will be change which you not in your control. So in such a situation, when there is a change, and it unfortunately also leads to a fade during that period, then there is some complications with that. But several students had asked, and I'm very glad that you asked, because that gives us a chance to clarify and build on that in today's lecture. So here is our explanation and insight into the methods. So the way the data would be transmitted, user data segments interspersed with overhead, and we often call it as a training sequence. And what is it that you're training? Why the name training? Because you are doing channel estimation, and usually this estimation is done using an adaptive algorithm. And adaptive algorithms, you go through a process called training, and that's why it is called a training sequence. So adaptive channel estimation is what you would typically use, and that would be also known as training of your channel estimates. So that is why the original name comes from, but again, it's overhead. You don't want to put too much of overhead because that will reduce your throughput. So you want to keep the overheads as minimum as possible, but at the same time, you must make sure that you have good channel estimates and reliable methods. Okay, so let me just write down a few equations to remind us of the process that we are going to follow. So the received signal, I'm going to write it in terms of the sampled notation. So Rk stands for R of t sampled at the kth time instant. So at time instant k, I'm not going to use the continuous time notation. I'm going to use R of k. This is going to be Zk, that is my channel coefficient sampled at that point. Sk, that was the symbol or the transmitted signal at the kth instant of time, given adding with the noise sample at the kth instant of time. Okay? So this is the framework. So Zk actually represents alpha k e power j phi k, and for coherent detection, I must have a good estimate of this. This is needed for coherent estimation, needed for coherent detection, and that is what we have indicated for coherent detection. Because if you don't have a good estimate of alpha and phi, then you will make a mistake in your estimate of SK, and then that would lead to poor performance. Now, I would also like to tell you how actually coherent detection is carried out. It is actually carried out as a two-step process. Okay? The first step, so step 1 is called channel estimation. Channel estimation. And that is what happens when you have given some number of known symbols called the training, and you estimate the channel here. Now, at the next time the occurrence of the training or the overhead, you can estimate the channel again. Notice that there is some variation in the channel. So, the estimate of the channel, let us say, was something of this type. Okay? Some variation in the channel is present. So, when you want to have very good performance in terms of your bit error rate, and you have a dense constellation, for example like 64 QAM, the even slight variations in the amplitude and phase will make a difference. So you want to, this channel estimation is good, but you must also follow it up with a step 2, which is called channel tracking. You want to keep track of what changes are happening in the channel. Okay, now this is very important, and again it's a very simple concept. Let me just explain it to you in the following graph, or in the following steps. Okay, so time index 0, k equal to 0, that is my starting point. What is known at this point? I know R0, that is what is obtained, and through the channel estimation process I know alpha 0 e power j phi 0, correct? That is known for me. Now, that is my initial estimates. Then comes the time index 1. What is known at this time? I know R1, I know alpha naught e power j phi naught. That was my channel estimate that was given to me. Now, the first data symbol has arrived, that is represented by the sample R1. Using these two, I estimate the first transmitted symbol, S1 hat. That's the detection process. That basically you plug into the equation that is in the previous one. Now, what is channel? This is detection of the transmitted symbol. Now, the tracking of the, take R1, take S1 hat, and obtain alpha 1 e power j phi 1. That means you assume that the channel will change between symbol 1 and symbol 2, and you have already detected symbol 2. So this is S1, this is S1 and S1 hat, and what we are doing is trying to estimate what is, slight change has occurred. This is alpha 0 e power j phi 0, this is alpha 1 e power j phi 1. So there is a second step that you do at time index 1. Okay. Then go to time index 2, let me use a different color, time index 2, I use R2, I use alpha 1 e power j phi 1, that will give me S2 hat. A second step at this point, which will be R2 combined with S2 hat, those are the known quantities, and what I am going to estimate is alpha 2 e power j phi 2, and then this process is repeated. Okay. So notice that you do estimation of the symbol, you do tracking. Again, this was something that just did not wanted to get into the details, but this is how coherent detection is done, especially when your channel is changing and you want to keep track of those small changes in amplitude and phase so that you can get the best performance out of your system. Okay. Now, everything is going fine if your estimations are correct. So I put tick, that means those estimates are correct. So therefore, my process completes and I get 0 bit error rate because I have been able to estimate. Now, unfortunately, if it turns out that, let us say that one of these was wrong, let's say S2 for whatever reason because of the noise sample was wrong, where will it affect me? It will affect, this one will also become wrong because it's going to update in the wrong fashion because S1 is wrong. this one is wrong, so this is wrong. So because this is wrong, that means this one is wrong, so this is most likely going to be wrong also. Now because this is wrong, this is wrong, this is going to be wrong also. So notice that there is going to be a cascading, or what we call as a propagation of error, because one leads to error in the other. Now this is what we are worried about, because between these two channel estimates, let's call this channel estimate number 1, this is channel estimate number 2. Let's say that the signal momentarily went into a fade. All it needs is for you to make one symbol error, and then slowly the error. So the detection errors was what I had drawn in the previous graph. The bit errors, no errors until you got into the fade situation. But once you hit the fade, what happened? Your channel tracking got out of, basically out of in terms of, started making errors. And because your channel tracking started making errors, your decision started to be wrong. And therefore, beyond that point, error basically keeps piling up, and you don't have a way of recovery until you get to the next training section where you can re-estimate the channel. Okay. So I hope now this graph become a little bit clearer, because yesterday, just with this explanation, I think several students had doubts. Channel estimation, channel tracking, why is channel tracking needed? What happens? Why does error propagate in channel tracking? And how are some of the issues that we need to deal with? Okay, so the two scenarios that can happen is that the fade occurs between the two estimates. That is what I have shown here. So that is, let's call that as scenario 1. This is scenario 1. You probably will be able to detect until the fade occurs, and then after the fade, we don't know. You may or may not have recovered, and therefore there could be errors in that situation. A more serious problem is what happened if the fade occurred during the training sequence. Then you made error in your initial estimate. So which means that the entire data after that is questionable, because your entire burst may be wrong, and that is something that could severely affect you in terms of your performance. So these are some of the practical issues with the coherent detection method. And notice we are going back and forth between channel estimation and channel. Basically, at this point, we do channel estimation, initial channel estimation. Initial channel estimation. Okay, initial channel estimation is 1. And during this process, during the data portion, we do what is called decision directed channel tracking. I'll just explain that. Again, many of you will be familiar with it. Decision directed channel tracking. That's another way of saying that my decisions are used to keep making adjustments on my channel. Channel tracking. Okay, and that's basically consists of 2 steps. At each step, there is a symbol detection. That's a step 1 at what we showed, symbol detection. And then there is a channel tracking or channel updating. Channel tracking, and this goes back and forth. Okay, channel tracking or channel updating. And this is essentially what coherent detection is all about. There is an initial channel estimate, there is continuous tracking of the channel. In order for you to be able to track the channel, you must have known symbols. The known symbols, I use my decisions as my known symbols to do the updation of the channel, with the being very aware of the risk that if I have made a decision error, that could affect my channel update, and then that could lead to error propagation in my system. Question is, how do I know whether the estimate is correct or not? I have no way of knowing. So basically, I do the best possible estimate and then do my data detection, and at the receiver, hopefully if there are only a few errors, my error correction code would have cleaned it up, but there is a good chance that if there was a fade, like for example scenario 2 happened, then I may not be able to recover that particular burst. So those are the challenges that we face in a wireless system. I know what has been transmitted, so therefore why am I not able to estimate the channel correctly? So here is the Rk is equal to alpha k Sk plus eta k, correct? That's the equation. During training, I'm going to put a tick on what is known. This is known, this is known. What is not known? this is not known, that's a random quantity, this is not known. Now, estimation of the channel coefficients is done using the following assumption, that my noise can be neglected. I keep the received data, the transmitted data which I know a priori, and I estimate alpha k hat. Is that correct? Everybody is clear with that? That's how I do, because I don't know the noise and I have no way of estimating what was the noise sample. So I ignore the noise. Now what happens when you are in a fade? Alpha k becomes very small, but your the channel noise, which is controlled by sigma naught squared, has not changed. So therefore your signal to noise ratio is very poor. So where will it affect? It will basically affect in your estimate of alpha k, because you are assuming, you are ignoring the noise, but really the noise is a very significant component. So because you are ignoring something that is large, that is reflected in your channel estimate, and that is why you get a erroneous channel estimate when you are in a fade. The question is very valid, because Rk I have received, Sk I know what was transmitted. Why not? Why am I making a mistake in transmitting alpha k? Because I am ignoring the noise component. Okay, but a very good question. Now we would like to quickly introduce differential phase modulation. Again, I am assuming this is a topic that is familiar to you from digital communications. So many times we say differential modulation, it's more or less understood that we're talking about differential modulation of the phase. Let me quickly give you the differences between coherent versus differential. So conventional phase modulation. Conventional phase modulation on the left, differential phase modulation on the right. Okay, conventional phase modulation, again I'm following the sampled data notation. So which says at the kth time instant, I'm going to transmit e power j theta k. That is my information is encoded in the phase, which means that theta k is decided by the bits bk comma 0, bk comma 1. Let's take qpsk, only 2 bits are there. The bit 0, bit 1 at the time instant k determine what theta k is. Now sk minus 1, the previous time instant it would have been e power j theta k minus 1. The theta k minus 1 would have been decided by bk minus 1 comma 0, bk minus 1 comma 1. Okay, and let me just write one more because I need to have the full representation. K plus 1 e power j theta k plus 1. This theta k plus 1 determined by bk plus 1 comma 0, bk plus 1 comma 1. Okay, that is your conventional phase modulation. You will transmit this, receive it, and make the detection. After you have estimated theta k, you will then map it to corresponding bits bk. So the observation that I would like to make is that the information at time k, information at time k, time instant k, is in theta k. It is not in theta k plus 1, it is not in theta k minus 1, it is only contained in theta k. Now on the other hand, let's draw a line and then say what is differential modulation, differential phase modulation. Differential phase modulation. Again, this is probably something that is familiar to you, but let me just highlight that. So I still have to transmit phase information. So theta k is equal to theta k minus 1 plus delta theta k. So whatever was my previous phase, to that I add delta theta k, and in this case delta theta k determined by bk 0 and bk 1. Likewise, then what will happen? I will transmit the symbol sk e power j theta k. What is the transmitted symbol here? It's also e power j theta k. Both are e to the j theta k. Okay. Now let's look at theta k k plus 1. This would be theta k plus delta theta k plus 1. this is delta theta k plus 1, that is determined by bk, bk plus 1 comma 0 and bk plus 1 comma 1. Okay. So now what notice, sk plus 1 is equal to e power j theta k plus 1. Previously the information was contained only in theta k, but now the information here, the information for us, information at time k, at time k is in delta theta k, delta theta k. But delta theta k introduces a relationship between sk plus 1 and sk, right, or in this case it will be sk minus 1 and sk. So delta theta k actually introduces some dependencies. There is a dependency between sk minus 1 and sk, and the relationship is sk is equal to sk minus 1 e power j delta theta k. Okay, that's another way of writing the same equation, delta theta k. This is the same as saying e power j theta k minus 1 plus delta theta k. Okay, notice that the resultant signal, the transmitted signal looks very similar, but in one case there is no dependencies between successive symbols. In another case there is a deliberate dependency that has been introduced through the modulation process. And again, I'm sure as you probably have studied before, there is a reason for doing that, and we will just touch upon the elements that are. But is the aspect of how differential information, encoding of information has been introduced. Is that clear? So now comes the detection part. So let me write down the differential detection when the information has been encoded differentially. So differential detection relies on the following two equations. Equation number 1 says Rk is equal to alpha k e power j phi k, that is my fading coefficient, sk plus eta k, that is equation number 1. Equation number 2, Rk minus 1 depends on alpha k minus 1 e power j phi k minus 1, that is my fading coefficient at the previous time instant, the transmitted symbol at previous time instant plus the noise nk minus 1, equation 2. We make one assumption in all forms of differential detection, and the assumption that is made is that the change between two successive symbols, and that is a very valid assumption, is that the channel looks almost the same. So if you call this as zk, this as zk minus 1, that zk is approximately the same as zk minus 1. That's an assumption that we are making. Under this assumption, we now do the following operation. The operation is rk minus 1 conjugate. I multiply the current received symbol with the previous received symbol, conjugate of the previous received symbol. If you just write down the expressions, that will be z sk plus eta k. I've made the assumption that alpha k and alpha k minus 1 are both represented by z. This would be z star sk minus 1 star plus eta k minus 1 star. That's the substitution of the two expressions. Okay. Now the expansion of this, very straightforward, but let me just highlight it for you. It would be mod z squared sk minus 1 conjugate, plus there are going to be 4 terms. The first one will be z times sk times eta k minus 1 conjugate. Next term will be z star sk minus 1 star eta k, and then the last term is eta k minus 1 star. 4 terms. Just substitution and expansion. Again, I'm sure this has been familiar to you, but I just want us to get comfortable with what the insights that we have as far as differential detection are concerned. Okay. Here is another assumption that is made. that is you have fairly high SNR or good SNR conditions. What does that mean? That the variance of the noise is much less than the signal variance. So in other words, I'm making a qualitative statement, eta k magnitude and eta k minus 1 magnitude are small compared to with respect to 1, because the magnitude of Sk is equal to 1. It's a phase modulation scheme, e power j theta is the transmitted signal. So the noise samples are small relative to this. Okay? If this is a correct statement, then the first approximation, the first thing that I do is to say that this thing can be ignored. Because it's a product of two small numbers, I can ignore it. Okay? Now, the first thing that next thing that I observe is this is the detection step that I need, because Sk minus 1 conjugate basically gives me e power j delta theta k. That's exactly what I need to detect. So yes, this is good. I need to keep that term. What are the terms that I don't want? These are the terms that I don't want. One of them is very small. The other two look like noise. Why? Because this is eta k conjugate does not matter, that also looks like noise. Eta k is noise. What is it getting scaled by? It is getting scaled by two quantities. One of them is a random parameter z, but we know that expected value of mod z squared is equal to 1. Basically that's you're looking at the case scenario where the Rayleigh fading with respect to the RMS value there is a certain expected value of z squared is equal to 1. And of course, magnitude Sk squared is equal to 1 because it's a phase modulation scheme. So if I'm looking at a normalized equation where expected value of z squared is equal to 1, then this is the same, has got the same statistics as eta k. Okay, as eta k. So what is it? What is eta k? It's noise of a certain variance which is related to sigma squared equal to n naught by 2, where n naught is your noise spectral density. So what does this type of operation do? It's called circular rotation. So you take some noise sample, conjugation flips it around. Zk and Sk are random quantities which will basically rotate the noise. So if the noise was originally pointing in a particular direction in the IQ plane, this random rotation moves it around somewhere else into the I plane, and it really does not change the statistics of the noise. So if this was eta k minus 1, this could be eta k minus 1 conjugate z times Sk. It's basically some sort of a random circular rotation of the original noise. So therefore it did not change the statistics. But very important to note that you are now going to be doing your detection not in the presence of one noise term but two noise terms. Okay? So this is the detection metric, and there are two noise terms. So roughly speaking, you have twice the noise in your decision statistic as you had in the coherent detection case. Would that be a good summary? So differential detection has been defined as Rk into Rk minus 1 conjugate. I expand the terms, I get 4 terms. One of the terms is negligible. The other 2 terms are noise with the same statistics as the original noise which was present in my system, but they are uncorrelated, so therefore I will get double the noise variance. And then I have my decision statistic, which is going up or down based on zk squared, but what I'm looking for is the phase. Any scaling of the phase is not going to matter. I will still get the angle as the one that I'm interested in. So this is the differential detection. So let me summarize. So let's write down coherent versus differential detection. Differential. Okay, this one would be Rk is equal to Zk e power j theta k plus eta k. This one I will do Rk minus 1 conjugate, and again based on that I will get an estimation of delta theta k, which is of interest to me. In this case, the decision that I need to make is on what is theta k. So that's the process that we are going to follow. So the first observation that we make about coherent detection is that I need an accurate estimate of zk, of both the magnitude and phase, alpha k e power j phi k. I need to know both of those. Now the question is, do I need to know anything about z? No. Though mod z square is present, it does not affect my angle, because I will take tan inverse of imaginary part by real part, so alpha square is not going to play any role. So I can safely say that I do not require any estimate, not required. That is, zk is not required. I don't need to make that estimate. So it makes a huge difference, because that means you are telling me that I don't need to worry about anything about the channel, whether it's fade, not fade, really does not matter. All I take is rk minus 1 conjugate, and I will be able to detect it. Another important difference is that I have one noise term in my decision statistic, one noise term. The variance is with variance sigma naught squared equal to n naught by 2, that is your noise spectral density. Okay. Now in this case I have two noise terms, I have to be careful with that. Two noise terms, the resultant variance will be 2 times sigma naught squared. So there is a penalty. So sometimes you will see people who make the following statement, there is a 3 dB penalty for differential detection. Where does the 3 dB come from? Because you have twice the noise, factor of 2 is a 3 dB penalty. So again, it's not a strictly correct statement, you just have to make sure that where the original impact is coming from. Okay, so given that these two are the issues, then here is the understanding of the performance. So here is the performance. Again, we have not yet derived the analytical expressions, but I'll give you something which will give you. So this is the performance in AWGN. AWGN performance of BPSK. So let us say that so this is AWGN performance of QPSK. Let's compare it. Now QPSK in fading. QPSK in fading. That is the graph. And because of the two noise terms, this you will have to take on faith, the performance of differential QPSK will look like this. It turns out that it's almost a shifted version. So DQPSK in fading. Okay, and of course these are the criteria. One requires ZK, the other one does not. One deals with one noise term, slight better performance, the other one has two noise terms, but this is the graph that you would. So the question is, why would you even bother with differential QPSK? Because if I have very high Doppler and I'm not able to track my channel, do you know what will happen? The bit rate performance of QPSK will start to do this. This is called an error floor. It's not because of your modulation scheme, it's just that your receiver is not able to track the variations in the channel. And under such situations, it's probably much better to go with DQPSK, because DQPSK does not care about the Doppler, because it's not trying to track the channel, it will give you a good performance. So now you know why you are even interested in differential detection. Okay? So I suppose you would summarize it by saying that the reason you would even consider differential detection, because it gives you a huge advantage in high Doppler environments. Advantage in high Doppler, it is also very low complexity. So if you want a low complexity receiver, so these are some criteria that you may want to consider why you would use a differential detection. What if my channel has ISI? Channel with ISI. Again, I will just frame the equation and frame the question and then leave it for you to discuss. So here is the channel received signal. Rk is equal to Z1 comma k at time Sk plus Z2 second channel coefficient at time k times Sk minus 1. I am just doing one symbol of ISI. So the current received symbol is some current received signal is a combination of the current transmitted symbol and the previous transmitted symbol, both of which are corrupted by complex coefficients Z1k and Z2k respectively, and of course there is noise which is eta k. And write down the equation for Rk minus 1. Rk minus 1 is Z1 k minus 1 Sk minus 1 plus Z2 k minus 1 Sk minus 2 Sk minus 2 plus eta k minus 1. Same equation like before, I am going to do that. Okay. Now, this will give me an estimate of theta k. Right? When I look at Rk, it will tell me what was the resultant theta k. Rk minus 1 will give me an estimate of theta k minus 1. Have to take the difference of these two, delta theta k minus theta k minus 1. This gives me delta theta k estimate, which will then get mapped to bk comma 0, bk comma 1. Those are the two bits that were transmitted. Again, the same framework, differential encoding, and this is the received signal in the presence of ISI. Again, the right hand part of this equation is from the previous graph. Now, without any hesitation, if we go ahead and say, well, I know what differential detection is, it is Rk minus 1 conjugate. Please write down the expressions. You will find that there are lots of terms. There will be 6 terms. One of them is your desired symbol. That is basically mod z squared sk minus 1 conjugate, plus there is a lot of terms which are, we do not know what to do with it, because there is one decision statistic. There are 5 terms which are treated as noise. Well, last time I took 2, this time 5. What's the difference? You know, no problem. Slight shift in the BER. Well, not quite, because take, for example, just the second term that is there in the one of the terms that is there in the expression. Okay, what you can get, for example, is Z2 comma k, Z1 k minus 1 conjugate, Sk minus 1, well, that's not a good example, Z2 k minus 1 conjugate, Sk minus 1, Sk minus 2 conjugate. Okay. Now, this is a term that has got magnitude squared approximately equal to 1, because that is a Rayleigh coefficient. This is a signal that is of magnitude equal to 1, Sk minus 1 conjugate. In fact, this is actually a useful information. It is, what is that? It is e power j delta theta k minus 1 is actually, but I am interested in detecting e power j delta theta k, and it so happens that delta theta k minus 1 is there in my expression, but I am not using that information. But the important thing to note is, if I treat this as noise, what happens? I have signal and I have noise of the same order of magnitude. What is SNR in that case? 0 dB. And if I have many terms like this, what will I get? I will get negative SNR. So, which means that this is disaster, not going to work. That is why ISI, if we go into channels with differential detection, this is not going to work. Okay. Now, one of the other combinations that we may ask the question. Okay, so then leave this aside. Now, can I do differential? Maybe write it on the next sheet of paper. I'll just summarize the points. Can I do differential modulation? That means I encode differential modulation, and can I combine it with coherent detection? Is it possible? Now, you may ask, why would I do that? But I'm asking a different question, not why can it be done? Yes or no? Think about it, you will tell me the answer. Okay? Now, the other aspect, so this is very important element that we would like to, so there is the issue of channels with ISI, their differential detection is not going to work. So that's a big no. No. But this is a possibility. Now I want to ask you even one more possibility that you may not have thought of. This is at least many people would have thought about this. I want to ask you the question, if I have coherent modulation, can I do differential detection on that? Differential detection. Okay, if you can answer these two questions, we have fully covered our understanding of differential detection and all the pros and cons. Where can we use it? Where can we not use it? Where are the advantages? Where are the disadvantages? So please attempt to answer these two questions. It's actually one line for both of those, and it's very, very easy to get the answer. But I would like you to think about it. We pick it up from here. The next thing that we are going to be looking at is the analytical BER. So if you have studied this before, please refresh your memory about how the analytical BER is derived for the different modulation schemes. We would like to look at it in the context of fading. Thank you.